We've previously spoken about general molecular movement across biologic membranes, but I'd like to now focus on the movement of ions specifically across those membranes. We've spoken before about how small nonpolar molecules like gases and steroid hormones move through membranes by simple diffusion. Small polar molecules like water are able to move across membranes by facilitated diffusion through channels like aquaporins. Larger polar molecules, like glucose for example, must be transported by carrier proteins across biologic membranes through either facilitated diffusion or active transport. Because of their charge, ions are unable to move through biologic membranes without the help of transporter proteins, either carriers or channels, using active transport and facilitated diffusion. I'd like to focus on two ions specifically, potassium and sodium, because they contribute to biologic function. In general, when thinking about molecular movement across membranes, we think about the concentration of a specific molecule on both sides of the membrane. That allows us to determine whether or not the molecule will have any net movement across the membrane, and if so, in which direction that net movement might be. When considering the movement of ions, we also have to consider the concentration of a specific ion on both sides of the membrane, but because ions are charged, we have to consider their charge as well as the charge of the environment on both sides of the membrane. Most often, the extracellular environment carries a positive charge relative to the negatively charged intracellular environment. When looking at, in panel A, a positively charged ion, it would want to move from the positively charged extracellular environment to the negatively charged intracellular environment because those opposite charges are going to have an attraction for each other. In this way, movement from the positively charged extracellular environment to the negatively charged intracellular environment, a positively charged ion would be moving with its electrical gradient. In panel B, moving that same positively charged ion from the negatively charged intracellular environment would necessitate the input of energy because the ion would be moving against its electrical gradient. Let's first consider the movement of ions through ion channels. Movement of ions through ion channels is going to occur by facilitated diffusion. Ion channels, like the potassium ion channel shown here, allow for only specific ions to move through them. In this way, ion channels are selective. The selectivity filter shown here is allowing only those positively charged potassium ions to move through because the size of that pore, as well as the amino acids that line that pore, will allow only for a positively charged ion approximately the size of potassium to move through. Of course, anything positively charged that's smaller than potassium could also move through this selectivity filter, but not something larger nor something negatively charged. I also want to point out that while there is a pore through the membrane, that pore created by an ion channel is not consistently open. It's possible to close a channel, and in this way, ion channels are considered gated. There are a number of different things that can open and or close ion channels. Beginning with the right-hand side of this image, we see that some ion channels are mechanically gated, meaning that stresses, physical stresses placed upon a cell or a cell membrane can tug on the shape, if you will, of a mechanically gated channel to cause that channel to open or close. One example of a mechanically gated channel is in the auditory cells of our ears. Sound waves cause those channels to open or close, and that allows our auditory neurons to respond to sounds. In the middle, panels B and C demonstrate that ion channels can be opened or closed based upon the binding of some molecule. Ligand-gated channels can have the ligands binding to the extracellular face of a channel or the intracellular face of a channel. In either case, molecular binding causes a shape change that opens or closes an ion, a ligand-gated ion channel. Finally, shown in panel A, ion channels can open or close dependent upon the charge distribution around them. These are termed voltage-gated channels. When the membrane voltage changes, the shape of the ion channel changes as well, and that causes the ion channel to open or close. Ions will move through open channels, and that movement is by facilitated diffusion. Because we're talking about diffusion, ion movement is going to be in the direction that is overall energetically favorable, meaning that both the chemical and the electrical gradients must favor movement. It's not that simple, however. While ion movement is governed by the electrochemical gradients on either side of the membrane, ion movement will also change the electrochemical gradient because we're talking about the movement of a charged particle. Let's see how this might work. Looking at panel A on the left side of the slide, we see that there are both positively and negatively charged ions on either side of the cell membrane. We're going to consider the left side of the membrane as the outside of the cell and the right side of the membrane as the inside of the cell. Because there are an equal number of positive and negative ions on either side of the membrane, there is an exact balance of positive and negative charges on both sides of the membrane. In this case, we're saying that there is no charge difference across the membrane, so the membrane potential is equal to 0. Membrane potential is defined as the charge difference across a cell membrane. Considering panel B on the right side of the slide, again with the outside of the cell to the left of the membrane and the inside of the cell to the right side of the membrane, if we move a few positively charged ions from inside of the cell to outside, now all of a sudden the outside of the cell is more positively charged than the inside of the cell, which is more negatively charged than the outside of the cell. This sets up a charge difference across the membrane, or a membrane potential, that is not 0. Indeed, the outside of the cell is positive relative to the inside. Because we consider our world relative to the inside of the cell, we say that there is a negative membrane potential. There is more positive outside, more negative inside. The charge difference or membrane potential across the plasma membrane of most cells is primarily due to the movement of potassium ions. That movement is going to be from inside of the cell, where potassium is more highly concentrated, to the extracellular environment where potassium is in low concentration. That movement will be through potassium leak channels, potassium channels that are open, allowing for potassium to move freely across the membrane. While potassium's concentration gradient would want it to move from inside of the cell to outside of the cell, we also must consider potassium's electrical gradient. Remember that the inside of the cell is negatively charged, and in that negatively charged environment, the positively charged potassium ion is quite happy. The positively charged potassium ion leaving to the extracellular environment where it is positive is maybe not so great. So potassium is in what I call a conundrum. It wants to leave to follow its chemical gradient, its concentration gradient, but it wants to stay where it's negatively charged. Moving outside of the cell would be against its electrical gradient. Allowing potassium leak from inside the cell to the outside of the cell allows potassium to reach an electrochemical equilibrium. That electrochemical potassium equilibrium allows for the membrane potential of most cells to be positive on the outside and negative on the inside. To summarize, the movement of ions across cell membranes sets up a charge difference or voltage across the membrane. That charge difference is known as the membrane potential. The membrane potential is measured in millivolts. The membrane potential of a typical resting cell is around negative 70 millivolts, and the negative refers to the more negative on the inside of the cell. A membrane potential can change if ions are moved in either direction across a membrane, and that might occur if an ion channel opens or closes. Excitable cells, like muscle cells and neurons, become excited when the charge distribution or voltage across the membrane changes rapidly. Here is a key point. Those excitable cells respond to changes in voltage across the membrane because they have voltage-gated ion channels. Finally, the voltage across a membrane of a cell can be calculated if you know the ion concentrations on either side of the cell, outside and inside of the cell. And of course, you must make some assumptions. We'll talk about how to do that in the next couple of videos.